Hi everyone. So in this lab, we will be going to design RTL to GDS, where RTL will be the Verilog code which we will be writing, and the GDS is the graphic design system 2 file, which is the mask-friendly floor plan, where this GDS will be sent to the foundry so that this can be fabricated. So in order to start with RTL to GDS, which is the ASIC flow, what we will do is we need to first write the RTL. Now here the RTL is written as a up-down counter. So the first lab, we will be going with the 4-bit up-down counter. So this is the RTL which we need to write. And this RTL needs to be validated in Vivado so that the functionality of the written RTL or the Verilog code is perfectly fine. So once this is done, you create a folder on your server and just create these files counter.v the net rtl.v and a constraints file. So first we will write it in the form of txt. You can create this file by copying from anywhere because here there is no option for creating a file. So you just create these two files, and the process libs, the slow lib and fast lib, can be taken from the digital folder of the uh, technology library. Once this is done, what you need to do is just check whether the RTL which you have taken from the Vivado matches with this RTL. You can just copy paste from there to here. Next, you need to write the constraints file. So what are the constraints? Constraints are nothing but it is the definition for the inputs as well as the outputs, including the clock. Here the constraints, this since this is a small example, uh, we can just write the create clock name clock with the period of 10 nanoseconds and get ports clock. If this is a virtual clock, you will write create clock name virtual period some 10 nanoseconds get ports clock, and rest is all inputs. You can set the input delay, output delay, max and min. Next, the clock uncertainty, slew rate, slack, and everything you can write here. So since this is just a small counter, so we have written only few constraints for this particular counter. You need to save this file. After saving, you rename this file to the sdc.sdc, since sdc is nothing but the synopsis design constraint. So this constraint file will be given as the input for the genus as well as to the innovus. Now this counter, sdc, and the process libs uh, will start the genus commands. So first right click and open in terminal. Click on open in terminal. Here press ls. While pressing ls, this will show how many files are editable or readable in this particular folder. If the files are not in this particular green color, then what you need to do, you need to type chmod 777 and that particular file name and press enter. This will make the file as a readable, that is to the color green. Now what you'll do is you just type genus in order to invoke the genus tool. As you can see here, as the genus is already invoked, you will get a command line as at genus root 1. So from here, our genus tool starts. First, what we will do, we will read the library file by typing read underscore lib space. We will take the slow process, type slow.lib and press enter. This will start reading all the uh, related library areas from the slow.lib. Now we will input it the HDL file by typing read underscore HDL space our .v file. I'm sorry, read underscore HDL space counter dot v. So this has read the RTL file. Now what we will do, we will type elaborate. So this elaborate, we will create, it will create a file where it will be starting to check the analog nets. It will be checking the source of the RTL. It will be checking how many number of MUX or LUTs or any other registers need to be put or mapped. Also, how many number of IOs are there, as well as how to map it with the standard cells. Later on, what we will do is we will give our constraints file by typing read sdc space constraints.sdc. Press enter. Here you can check the constraints, whatever we have written. All the related constraints have been passed. If any of the constraint is not matching, it will show it in the failed context or the failed content. If the SDC file is correct, then it will say it is successful. Okay. Now what we will do, we will generate the synthesization process by typing the command as syn underscore gen. What this will do, this will start the synthesizing of the RTL. Now we will type syn map, syn underscore map. So this particular command will map all the standard cells which are related to that particular RTL, and it will be storing it in the form of a synthesized format. Now what we will do, we will optimize our design by typing syn underscore opt. This will optimize the design by taking fewer number of standard cells, the lesser number of vias and routing and everything. Now, since all this is done, this will show that all computer switching activities are removed. Resetting power analysis results, rewritten the formal verification information, and done the mapping. Since you can see synth 5 info done the mapping. This shows that your RTL is being synthesized properly. Now what we will do, we will write our netlist. You can write netlist by typing you can write the netlist by typing write underscore HTL, the greater than symbol, and any file with .v extension. Since this is a netlist, I am typing it as a netlist.v. So this is write HDL greater than symbol netlist.v. This will write, again I'm sorry, write underscore HDL greater than symbol netlist.v. So this will create a netlist file. If you see this netlist file, this will contain your module, the name which you have given, the inputs and outputs, and the required wires. Okay, and these are all are the standard cells which are taken from the library. Okay, so this has completed your synthesizing of the netlist. Now, in order to check your synthesized RTL, you can just press the command of GUI underscore show. So you will get a GUI like this for the genus. Here you can find the up down counter. Okay, just right click on this, go to schematic view module and select in main. So here you can see that whatever the RTL you have written is being synthesized and it is being mapped like this. Here if you zoom in, you can see these are the standard cells. Okay, so this is the GNS part which is done. Later on, the netlist which is generated in the genus will be given as a input to the innovus file that we will see in the next video. Thank you.